In this session, we discuss about a few topics about channel coding. First, we discuss about channel coding. Then we move to what are the different types of channel codings are available in the wireless communication by considering a suitable examples. Before that, channel coding refers to the class of signal transformations designed to improve communication performance by enabling the transmitted signal to better withstand the effects of various channel impediments such as noise, interference, and fading. These signal processing techniques can be through of a vehicle from accomplish desired systems trade-off like error performance versus bandwidth, power versus bandwidth. Why do you suppose channel coding has become such a popular way to bring out about these beneficial effects? The use of large-scale integrated circuits and high-speed digital signal processing techniques have made it possible to provide as much as 10 dB performance improvement through these methods at much less cost than through this out of most methods such as high power transmitters or larger antennas. Channel coding can be divided into two areas. In the first one, waveform coding, and the second one, structural sequence coding. Waveform coding deals with the transferring waveforms into better waveforms to make the detection process less subject to errors. Structural sequence deals with transforming a data sequence into better sequence, having structural redundancy. The redundancy bits can be used for detection and correction of errors. The encoding procedure provides the coded signal with better distance properties than those uncoded counterparts. Here we discuss about different types of second category codes, that is structural codes, which is used in wireless communication. In the structural code analysis, we have different types of codes mechanisms to provide the ability of error detection and correction. Here, channel encoder adds some redundancy bits to the input bit sequence. Addition of these extra bits. This addition of extra bits allows the receiver to perform error detection and correction. However, increase the bit rate and hence increase the required bandwidth. If you add some excess bits, it also change the bit rate and also increase the required bandwidth. Now, coming to the different types of error control methods used in wireless communication. Error detection and retransmission based. In the first one, error detection and retransmission based. The receiver doesn't attempt to correct the error. The receiver simply requests a retransmission and require full duplex connection. Here the example is automatic retransmission request, we can be called as a ARQ protocol. And the second one is feed error correction. In the feed error correction, the receiver can correct and detect the errors, but it is simplex connection. Example, block codes and conventional codes. Coming to the compare with the error detection and retransmission, forward error correction is somewhat better efficiency because if the particular data is loses, again we go for the retransmission. Due to that, time taken for the communication leads more time compared to the error correction, forward error correction methodology. So maximum of receivers now we are developed based on forward error correction methodology by using of block code and conventional codes. Now we move to the different types of forward error correction codes. In the forward error correction code, the category number 1 related to the linear block code. In the linear block code, the information bit stream is divided into k blocks. Each block is encoded to a larger block of n bits. The coded bits are modulated and sent over a channel. The reverse procedure is done at the receiver. That means here we are adding some excess bits to the information bits. See here example, data block consisting of a k bits and it is moved to the channel encoder and there is a forming of a code word containing of n bits. And the structure of a code word containing n minus k number of a parity bits along with the message bits. Once again I repeat, the structured code word outcome containing n minus k number of parity bits and k number of message bits and complete the code word length is equal to n bit. Suppose if you consider 7, 3 code word. In the 7, 3 code word, the total bit code word length is 7 and k number of a message bits and 7 minus 4 that is 3 parity bits are adding to the information bits. That is the one example of linear block code representation. In the linear block code, error controlling coding that can be done by these following steps. A linear block code generates a block code of n coded bits from the k information bits. So already told that it can be represented as a n comma k binary block code. Example like 7, 3, 5, 2, 3, 1 binary code block code examples. After that, the n code word symbols can take on 2 power of n possible values corresponding to all possible combinations of the n binary bits. And after 2 power of k code words from these 2 power of n possibles is to be selected to form a code such that each k bit information block is uniquely mapped to 2 power of k code words. The code word is said to be linear if addition to any code words of this code produce a third code word in the code. Once again I repeat, a code word is said to be linear if addition of any two code words in the code produce a third code word in the code. A code is a systematic code if the first k elements in the code word are the information bits. Once again I repeat, a code word is a systematic code if the first k elements in the code word are information bits. Coming to the linear block code representation, the encoding operation of a linear block code is involving the two operations. In the first one, segmentation of information of sequences, and the second one, transformation of each message block into block of n bits according to the same predetermined set of rules. Once again I repeat, here there is a two operations are involved. In the first one, segmentation of information sequences, and the second one, transformation of each message block into a block of n bits according to the some predetermined set of rules. Now consider the example, message block of m is equal to m1, m2, so on mk. Each message bit can 0 or 1, that implies 2 power of k distinct message blocks. Suppose example, if you are consider 2 bits, there is a possible to generate 4 combinations, that is 0, 0, 0, 1, 1, 0 and 1, 1. Each message block is transmitting a code word of length of n bits, that is C is equal to C1, C2 and so on Cn. After that, there will be a 2 power of k distinct code words, one unique code word for each distinct message. Suppose example, C is equal to C1, C2 and so on Cn is consisting of a initially parity bits followed by the message bits. Suppose example, if you are consider a simple message like 1101, in the first 2 bits can be considered as a parity bits Next 2 bits can be considered as a message bits considered as an example. But there is some particular procedure to measure the parity bits and formation of code word. Here there is a linear block code with a systematic block code representation in a polynomial way. C is equal to P11 M1 plus P12 M2 and so on P1 n minus k into Mk, and followed by C12 Cn minus k, that is equal to Pkm and so on up to Pk n minus k Mk. Based on all these, we can draw one particular matrix form followed by message along with the parity bits, that including C is equal to M1, M2 and so on Mk, followed by the parity bits and followed by the one identity matrix. And it can completely represent as a C is equal to M into Z. G is called as a generator matrix. So the generator matrix is the combination of a parity matrix, that is P, followed by the identity matrix I. It can represent as P11, P12 and so on P1 n minus k, and P21, P22, P2 n minus k, and so on Pk1, Pk2, Pk n minus k, followed by the one identity matrix. And it can be represented as a reference format G is equal to matrix of P I k, but notice that the order of a generated matrix must be k by n. Already we noticed that n comma k is the linear block code representation. Based upon n value and k value, we have to decide the value of a generator matrix G. And k is identity matrix with the order of k by k, and P is the parity matrix order of k by n minus k. The generator matrix is a compact description of how the code words are generated from the information bits in a linear block code. Once again I repeat, the generator matrix is a compact description of how the code words are generated from the information bits in a linear block code. The design goal in linear block codes are to find generator matrix such that the corresponding codes are easy to encode and decode and have powerful error correction and detection capabilities. Of course, there is a trade-off between efficiency, reliability, encoding and decoding complexity. There must be a trade-off between efficiency, reliability, encoding and decoding complexity. After that, we have to find parity check matrix called as H. Associated to each n comma k, the linear block code have a parity check matrix H at the decoder. H is equal to matrix of identity and followed by parity transpose matrix P transpose. But notice that the parity check matrix with the order of n minus k comma n. After find the parity check matrix H, its rows orthogonal to rows of G such that G multiplication of H transpose is equal to 1. That means the parity check matrix of H and rows of a generator matrix must be equal to 0. The parity check matrix H is used to detect errors in the received code word. Once again I repeat, the parity check matrix H is used to detect the errors in the received code, where C is the code word in n comma k block code generated by generated matrix C H transpose is equal to 0. C multiplied by H transpose is equal to 0. And after that, let us consider R equal to C plus E to be the received message, where C is the correct code word along with the error E. Decode the operation is done by determining a syndrome vector called S. S is equal to R into H transpose, that implies E into H transpose. where all is the valid vector, then syndrome is received vector S is 0. Non-zero of S indicate there are errors in the transmission. That means once we calculate the value of a syndrome, if it results non-zeros, we find is that there is errors in the transmission. Thus error, if suppose S is used to detect the errors, it can also need to correct the errors. The errors can be corrected at the receiver by comparing S with rows of H transpose and corresponding ith received bit if S matches with the ith row of H transpose. The process of linear block code followed by message. We have to consider the message. Based upon the message, it will forming a generator matrix. By combination of a message and formation of a generator matrix, finally it will create the code word. Then the code word is given to the receiving section, and here in the receiving section there is a called a parity check matrix help. By considering the parity check matrix help H transpose, we have to find the value of a null vector, and all the procedure we have to take an example below. Let us consider a 6,3 linear block code with a generator matrix G. Then find all the distinct messages with a generator matrix G 110 100 011 010 101 001. We notice that G is the combination of a parity and identity matrix. Here there is a 6 by 6 order. In the 6 by 6 order, first we have to find 3 messages are formed. Why? Because the block code is 6,3. That means there is a 3 parity bits, 3 message bits, and the total code word length is equal to 6. Why? Because n comma k, we notice that in the n comma k, n minus k number of a parity bits, and n is the total code word, and 3 message bits and k message bits. So similar to that, here n comma k is compared with 6,3. In that 6,3, 6 is the code word length and 3 is the number of messages, and 6 minus 3, that is equal to 3 number of parity bits. So we finalize that the message vector is starting from 3, but mean there is a formation of 2 cube, that is 8 combinations starting from 000 to 111. 111. So consider the message and consider the code word. Consider the message 100 and consider the code word, and by considering of all message vectors, then once declare the message vector and code word, move to the next step. Now by using of generator polynomial, we have to design the parity matrix. In polynomial form of code word, C of x can be written as C of x is equal to m of x and g of x, where m of x is the message polynomial and g of x is the generated polynomial, and g is the generator matrix. Of course, we have to represent the generator matrix as well as in the generator polynomial. G is equal to followed by P and identity matrix, and we know that P is the parity matrix. In the example 2, we have to find a linear block code of G if the code generator polynomial G of x is equal to 1 plus x cube for a 7,4 code word. Here we notice that the total bits is equal to 7. K is the number of information bits, that is 4. Now number of parity bits are n minus k, that is equal to 3. And we notice that G is the combination of P and I. So make it form P followed by the identity matrix. Now we have to calculate x of n minus k plus I minus 1 divided by g of x. We have to find the remainder of x of n minus k plus I minus 1 divided by g of x for I equal to 1 to and so on k. And here we calculate parity, remainder of x cube followed by 1 plus x cube. You will get the remainder is 1 plus x, that is 110, and after that P2 that is the remainder of x power of 4 divided by 1 plus x cube. You get the remainder is x plus x square, that is 0, 1, 1, and followed by p1, p2, p3 and p4, and finally we got the generator matrix, that is 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 1. So we notice that here first 3 columns are related to the parity matrix and last 4 columns are related to the parity identity matrix. Why? Because G is the combination of a parity matrix and identity matrix. Now go to the one more example. Suppose that the code word U is equal to 101110 is transmitted. The vector is received 011110 is received. That means here there is a one error. The error in the first position. Why? Because we are transmitting 101110, but we are receiving 001110. That means leftmost bit is received error. Find the value of a syndrome. S is equal to R into H transpose, verified equal to EH transpose or not. With a H matrix is will given 1 0 0 1 0 1 0 1 0 1 1 0 0 0 1 0 1 1. So before starting the sum, we have to discuss some important terms. Hamming code or weight code we can be called number of non-zero components in the code. Hamming code or a weight of a code vector is called as number of non-zeros on the code word. Here we also find the distance, we call it as a Hamming distance. Hamming distance between the two code words is the number of components in which they are differ. And after that we have to find the minimum distance. The smallest distance between any pair of code words is also called as a code. Here the ability of code to detect and correct the errors can be specified in terms of a minimum distance of the code. Here one theorem we can be called as a linear block code theorem. The minimum distance of a linear block code is equal to minimum weight of any non-zero code word in the code. Once again I repeat, the minimum distance of a linear block code is equal to the minimum weight of any non-zero code word in the code. Here we can send the example number 1, the code word and minimum distance of the code. Here there is a one more theorem in the linear block code. The linear block code with a minimum distance of dmin can detect up to dmin minus 1 errors and correct up to dmin minus 1 divided by 2 number of errors, where dmin minus 1 divided by 2 denotes the largest integer not greater than the dmin minus 1 divided by 2. Coming to the proof, let us consider C bits to be transmitting in the code word and R bits can be received in the code word. Let us see any other code word in the code. The Hamming distance between the code word DC and C bar and DCR and DC bar and R satisfy the condition DCR plus the difference of C bar n must be greater than D of C and C bar. Let us receive a vector consisting of errors and dmin, the minimum distance of the code word must be greater than dmin. Then we have to discuss a new category of codes that is called as the Hamming codes. Hamming codes are the subclasses of a linear block codes. It consisting for single error and detection for the perfect code. To correct a single error, LBC must have minimum distance is equal to 3. The linear block code at a t equal to 1 and dmin is equal to 3 is called as a Hamming code. That means linear block code having the minimum distance is equal to 3, proportionally it is called as a Hamming code. Hamming code having the below attributes like number of parity bits m must equal to n minus k greater than 3 and code word length n is equal to 2 power of m minus 1 and number of information bits are k, that is equal to 2 power of small m minus 1 and the minimum must be distance is equal to 3 and error correction capability must be equal to 1. Hamming codes is the simplest to connect compared with the linear block code. Design a n comma code. Process of to design n comma code. The number of a code words is 2 power of k. The all zeros vector must be one of the code word. The property of closure must be applied and the sum of any two code words in the space must be held a valid code word in the space. Each code word in the n bits is long. Let us consider the dmin is greater than n into 2 power of k minus 1 divided by 2 power of k minus 1. The weight of each code word must be equal to at least 2 power of n. Assume that the code is systematic and the rightmost k bits of each code word and the corresponding message bits. Example, here we consider for 6, 3 code words, the generated matrix they are given 100, 101, 010, 001, 001, 100. Here we get the value of a minimum distance is equal to 2. Here we have to find the code word corresponding to the each distant message, verify the code word in a single error detection correction, draw the encoder circuit and determine the syndrome for the receiving message 101101 and also realize the circuit encoder. Coming to the first one, we have to find syndrome patterns for the received message 100000011. The syndrome R is computed S is equal to R into H transpose. That means we have R is 6, 3. That means n comma we have to compare with 6, 3 n comma k. N is equal to 6 and k equal to 3. That means number of parity bits are 3. So we have to draw for 8 combinations. For each and every 8 combinations we have to draw the code word. So in that code word we have to take the code word is 11111011 into H transpose. You will get 110. Error patterns corresponding to the syndromes E is equal to 001000. Then the error corrected by the vector estimated, that is R plus E cap, that implies 1000011 plus 001000. You will get 101011. Cyclic codes form a subclasses in the linear block codes. Here the implementation of a linear block code is relatively simply for the single error and correction. However, it is too difficult for the higher order error correction. Cyclic code has a simplest mathematical structure that permits a design of higher order correction and detection of codes. The encoder can be realized by simply using a shift registers, and a binary code word is said to be a cyclic if it exhibits two following properties. First one is linearity, second one is the cyclic. Then what do you mean by linearity? The sum of any two code words is the code word is also one code. The cyclic shift of any code word in the code is also formed a new code. Once again I repeat, the sum of any two code words in the code is also creating a new code. That is called as a linearity. Already we discussed in the previous slide. And property of cyclic, any cyclic shift of the code word in the code is also creating a new code. That is the property, that is the second property of a linear block code. Here we consider the code vector in format of a polynomial by considering the different codes C of x, C1 of x and C2 of x and Ca of x. One of the interesting property of the code polynomial is that xi is multiplied by C of x is divided by x of n plus 1. The remainder is Ci of x. Here there is a divisional process is going on. X of n plus 1 is divisible by the code vector, and you will get the remainder of x of I C power of x divided by x of n plus 1. Here there is a one theorem, that is, if g of x is the polynomial of a degree of n minus k is a factor of x power of n plus 1, then g of x generate a n comma code cyclic code for each of the code polynomial can be generated as c of x is equal to d of x is multiplied by g of x, where d of x is a data polynomial and g of x is a generator polynomial with the order of k minus 1 and n minus k. There is a non-systematic form of cyclic code. Here we have to discuss the cyclic code in a systematic approach. In the systematic approach, the first k digital and data bits and the last n minus k digital bits are parity bits. That means here the code word is consisting of R0, R1, Rn minus k minus 1 followed by the data bits. Here R of x is a parity check polynomial. For a systematic cyclic code, the code word polynomial phi of x corresponding to the data polynomial d of x is given by phi of x is equal to x of n minus k into d of x plus r of x. Here the r of x is the remainder of x of n minus k multiplied by the d of x divisible by g of x. Now we have to design an example with the following of n comma k is 7 comma 4 with a generated polynomial 1 plus x squared plus x cubed with a data vector of 1 0 and 1 0. And we notice that g of x is 1 plus x squared plus x cubed and d of x is 1 plus x squared. Now we have to use systematic code expression c of x is equal to x of n minus k into d of x plus r of x, where r of x is the remainder of x cube of d of x divisible by g of x is equal to 1. Then x cube plus 1 plus x squared plus 1, you will get the code word is 1 0 0 1 0 and 1 0. It is a systematic approach expression. Now coming to the non-systematic approach expression, phi of x is equal to d of x is multiplied by g of x. You will get 1 plus x squared multiplied by 1 plus x squared plus x cube. You will get the code word is 1 0 0 1 0 1 0. So see that the code which followed by the systematic approach, the code we followed by the non-systematic approach will create the same values like 1 0 0 1 0 and 1 0. Generator matrix of cyclic code. Cyclic code is also described as a generator matrix followed by parity matrix and identity matrix. That is, the parity matrix is the remainder of x of n minus 1 divided by g of x and the second row and third row and kth row. So why we go for this example? Why we go for this analysis taken as example to easy to understand? Determine the generated matrix of 7 comma 4 of a generated polynomial g of x is equal to x cube plus x squared plus 4. That means we have to convert the polynomial into matrix again. There is a possibility to convert matrix to polynomial. There is a possibility to convert a matrix into polynomial into matrix. That means vice versa process. Now here take a cyclic encoder. One of the advantages of cyclic encoder is the encoding of and decoding can be implemented simply by using shift register and modulo 2 adder. A systematic code which involves the division of x of n minus k d of x by g of x can be implemented by doing a circuit consisting of a shift register with a feedback correcting according to the generator polynomial. Where there is a 1, there is a switch is on. Where there is a 0, the switch is off. It is a simple block diagram representation of a cyclic code encoder. Now, cyclic code encoder data. The polynomial plays a major role in the generator matrix of cyclic code. If we have generated polynomial g of x and n comma k is a cyclic code with a certain k polynomials, we can create the generator matrix. Syndrome polynomial of the received code word corresponding for error polynomial. Along with these particular linear block codes, we have different types of remarkable cyclic codes called as cyclic redundancy check, we can be called as a CRC, and Bosch-Choudhury Askeum BCH code, we can be called as a BCH codes, and Reed-Solomon codes. These are the different examples for the remarkable cyclic codes existing in the digital communication. Here there is one example on base of syndrome test. Observe the example. Simple. Suppose that code word u is equal to 10110 is transmitted, but we are receiving 00110 as we received. Already we discussed in the previous slide. Leftmost bit having error. To calculate the syndrome, verify E and H naught. We know that we are receiving message 0011110, and that can be multiplied by H transpose. Already we declared the H transpose in the above. That is multiplied by H transpose. You will get the code word is 100. That means we indicate already if the syndrome having the non-zero, there is a possibility in the receiving message. there is a possibility of error in the received message. So clearly we notice that the transmitting message is 101110, but the receiving message is 001110. That means the first bit, the LSB bit having the error. But you will get the resultant of S into S is R is equal to R into H transpose, you will get 100. And observe that 100 is the first line in the H transpose. See that first row in the H transpose. So that's why you move to the first position in the received message. In the received message, if it is 0, replace it by 1. If it is 1, replace it by 0. That means here the MSB bit is equal to 1, 0, you have to transfer into 1. Automatically the message is, automatically the error is corrected. Suppose take as one more example. If you multiply by the received message with the H transpose, you will get the resultant is equal to 001. That means 001 is the third row of H transpose. Make sure that if you move to the third position from the MSB, from the received code word, in the received code word, and make sure that if it is 1, convert into 0, if it is 0, convert into 1. Automatically, the particular message, remove the particular process, remove the error in the received message. Now, take as one more example in the error correction. Assume that received message is 100 and transmitting message is 10110, received message is 00110. The syndrome we are getting 100. In the tablet form, the error pattern of the syndrome is estimated 1000000. Then simply corrected vector R plus E cap, you will get 1011110. This is also procedure to correct the error, or if you move to the simple step, get the value of syndrome, check the value with the H transpose belongs to which row, and estimate the row value. Based upon the row value, move to the position from the MSB to LSB. Suppose if it is the 100, belongs to the third position from the MSB side. In the third position, replace as a 0. If it is 0, replace as a 1. If it is 1, replace it by 0. Here there is a one more example. Use the dividend circuit of the form of the figure v of x is equal to x cube plus x power of 5 plus x power of 6. With the generator polynomial is 1 plus x cube. Compare the circuit implementation to the polynomial division steps is performed by hand. The dividing circuit needs to perform the following operations with x cube plus x power of 5 plus x power of 6 divided by generator polynomial in form of q of x plus p of x divided by 1 plus x cube. For that, there is a procedure going on. Based on the polynomial, first design the polynomial decoder, and after that input there is a one tabulated form followed by input q, shift number, register count, and outcomes of the feedback. By chaining of the message from the input queue from 0 to 001011, observe the shifts and update the values of register in the content and get the what is the outcome from the feedback. Based on all this, we have to create a polynomial 1 plus x square plus x cube plus 1 by 1 plus x cube, and make sure that process is divisible order x cube plus x plus 1 divisible by x power of 6 plus x power of 5 plus x power of x plus 1. So you will get the remainder is equal to 1. And here there is one more example based on error probability and modulated and coded. A coder orthogonal BFSK modulated with the signal over a Gaussian channel. The signal is non-coherently detect and hard decision coding. Find the coded bit error probability if the coding is 7,4 block code if the received EB by N0. So we know that EB by N0, EC by N0 is equal to 4 by 7 is multiplied by 20. That is equal to 11.43. Then the coded is a non-coherent BFSK. We can relate the probability of the channel symbol error EC by N0 is similar to probability is equal to 1 by 2 exponent of EC by 2E N0. then 1 by 2 exponent of minus 11.43 divided by 2, you will get 1.6 into 10 cube. If it is another category of modulation scheme, the probability error formula will changes depend upon the modulation scheme. We go for the probability error calculation. So once we get the probability error calculation, the probability of decoding bit error is followed by p into 1 minus p power of 6, that is 1.6 into 10 to the power of 5. Till now, we discussed about the different types of structure coding techniques followed by the linear block code, cyclic code, systematic approach and non-systematic approach, the formation of a generator polynomial into generator matrix into generator polynomial, and discuss about parity check matrix, parity matrix, the orders of generator polynomial, order of a parity polynomial. So once the process is going on, we have to calculate the value of a syndrome. By using of a syndrome, we are calculating the error is present or not in the receiving message. So if there is an error is present, we do some operations to remove the error. It seems like as a Hamming code. And we discuss about some of the problems related to the syndrome calculation, code words calculation, code vector calculation, and linear block code generation. Thank you.